Hello, this is Daniel Kim,
And this is Benjamin Lee.
and we're going to talk about the tautochrone.
And then brachistochrone, which is two unique characteristics of cycloid,
So let us begin. So first of all is time it takes from the top to bottom.
which is tautochrone.
And first of all, we have to know the basic physics to solve this problem. And as you can see here, is mgh equals 1 FMV squared from the potential, conservation energy and kinetic energy and the potential energy, and letting that equal. And you can actually find the v, which equals square root of 2gh.
And in this case, the h, which is height, is gonna be y initial minus y.
And time equals, in this case, it's distance over velocity, because distance equals meters. If you just say that distance equals meters, velocity equals meter over seconds, thus meter over meter seconds will lead to second itself.
Yeah, cancel. Meter is gonna cancel out. We only get the second, which is time.
So now we are going to go into the hardcore calculus stuff. Well, kind of. So time equals the integral of the change in distance over the instantaneous velocity that it has. And so the first part is the change in distance, which is up top. And we can get this by using the arc length formula, which is the square root of the y component square plus the x component over square. And the instance velocity will be taken from the above equation, which is v equals square root of 2gh. And in this case, it's going to be square root of 2g y initial minus y.
So if we plug in like initial conditions, we're gonna get this equation. Yeah.
And it starts from 0 to pi, and I think we already explained this during our original presentation during the math open house. So we'll move on.
Yep.
And then it just simplifies, as you can see, and it some cancels out.
And we're gonna get square root r over g pi.
And you have to pay attention right now, because just remember this formula. Remember this little initial, because it's gonna come up again soon.
And we're gonna prove time it takes from anywhere to bottom.
So this one is going to be much more complicated than before. It's slightly, I guess, a little bit complicated because its initial point will not be 0 in this case. It's going to be a, which means that we have to
fix y location.
Fix the y initial to, instead of the original one, we have to fix it to r plus r cosine a. And thus we will continue our simplification, and we just keep going down.
Yeah, we are gonna face this like massive formula, but we have to use side problem. We have to know the side like equations to simplify further.
So some of the equations are sine squared theta equals 1 minus cosine 2 theta over 2, and then if you square root both sides, it's going to be sine theta equals square root of 1 minus cosine 2 theta over 2.
And also cosine 2 theta equals 2 cosine squared theta minus 1.
Thus, implementing all these little steps, little side notes into our equation, the conclusion will be square root rg integral of a to pi and square root of sine t over 2 over the square root of 2 cosine 2h over 2 minus 1. And
also we simplify further, and we have to face u substitution.
Which is so fun! Yay! Ew!
Yeah, so in this case, u is gonna be cosine t over 2 over cosine a over 2, and du is like derivative of u, which is gonna be sine t over 2 minus 2 cosine a over 2, which can be like simplified as minus 1 over 2 sine t over 2 over cosine a over 2. And also we're using u sub, we have to change the limit. So we just simplify when initial condition. So like when t equals a, we plug in a instead of t, so we're gonna get 1. And when we plug pi, we're gonna get 0. So this is our new limit. If we plug in this new limit and we simplify it, we're gonna get the same answer.
So told you to pay attention beforehand.
And this exclamation mark is not factorial.
It's just exclamation mark.
Yes.
Yeah. So that's the tautochrone, and
therefore, regardless of starting point, it takes same time.
Yes. Hello. We're gonna move on to the next part, which is the brachistochrone, and this work is derived from
Professor Nishiyama Yutaka
and from the Osaka University of Economics in Japan. So first, to begin, we have to know the Euler's language equation, and this equation, we can prove it. However, it's going to take another open house project to actually go in depth.
Yeah, so it's a very deep topic, so we're just going to use it, not prove it.
So for the sake of time, we're just going to use the whole formula. And so the initial condition came out to be, we're going to use the t, the time equals from
distance over instantaneous velocity. But
so,
yeah,
going back to the other tautochrone, it's the same basic idea, but instead of using the parametric
coordinate system, we're going to use Cartesians. And for arc lengths of Cartesian is going to be a little bit different, which is square root 1 plus dy over dx squared.
And the velocity will be square root of 2g of y initial minus y,
which is the same as before. So, and we need to specify the L, and L should be consist of x and y prime. But
however, there's no x in this equation function.
Yeah, in our function. So therefore, we can transform Euler's equation into this new form,
which is L minus y prime times the del L over del y prime equals the constant.
We're going to explain how did we transform this, because it's going to take a lot of time. So we're just going to use it. So if we plug in initial conditions, we are going to get this equations, but if we simplify this, we're going to get this. And
over here, y times 1 plus y prime equals 1 over 2g c squared. If you know the Coulomb's constant of k, and that k equals 1 over 4 pi epsilon 0, it's the same basic idea that we're just letting a kind of complicated constants equal to maybe simpler constants, just 2a.
And then if we isolate the y prime, we're gonna get square root 2a minus y
over y. And I hope you guys remember this equation, because I hope it shows up again. And as I said, Euler's equation is used for optimization, which means that it's going to show either the fastest or the slowest, or the minimum or the maximum point of the slope. So for here, for instance, because we use Euler's equation, this path is going to be the fastest. However, now we're trying to prove that the cycloid path is the fastest. So if we move downward, we are going to derive the above equation by the cycloid components.
So equation for the cycloid is x equals r times theta minus sine theta, and y equals r times 1 minus cosine theta. And then in order to get y prime, we have to use partial derivative. So dx over d theta equals r 1 minus cosine theta, which is y, and dy over d theta equals r sine theta. And then dy over dx is going to be dy over d theta divided by dx over d theta.
So for the next part, we squared both sides to simplify furthermore, because as you can see, if you just use dy dx, it's kind of complicated because there's sine theta and there's cosine theta. There's no cancellation between them. So if you square them both sides, we can see that r squared over 1 minus cosine squared theta over y squared can come out. And the cosine theta equals 1 minus y over r is
we derive this, we isolate the cosine theta here from this formula. And
it's quite amazing to see, because y component up top here was a y equals r times 1 minus cosine theta. And however, if we took the derivative of x, we found out that r is same as y, which is quite amazing. So using the same formula, we plug in cosine theta equals 1 minus y over r to the dy dx squared, and then we further simplified it to find 2r minus y over y. And because this was squared, we have to take the square root of the whole thing, which came out to be square root of 2r minus y over y, and that equals the dy dx, which is same as the y prime itself, and 2r, it can be same as 2a, the constant. Thus, it is the fastest path, and it equals the original optimization from the Euler's equation. And thank you for listening, and go Falcons!
Thank you for coming.
Go Falcons!